Hi everyone. Um, I have posted in the files section of our Canvas site a handout called the Adequacy of the Tree Method. And you may want to either print it out or have it on another screen, on another device, so that you can follow along with the handout as I start to go through it in this lecture. So I'm continuing our meta-theoretical interlude, and I'm going to prove the second thing that I mentioned we were going to prove. In the last lecture, we took a look at the language SL, and we saw that using just not, and or, we can express any truth function at all. We can find a sentence of SL that expresses any truth function at all. And that was kind of an interesting exploration because along the way we we convinced ourselves that there are actually an infinite number of truth functions, even though we're focused on 5 of them. And the character of that proof is interesting because it's a constructive proof. The proof actually gives you an algorithm for constructing the given any truth function, the algorithm gives you a way of constructing a sentence that expresses that truth function. So that was interesting. But what we're going to do now is we're going to turn our attention to the truth tree method. And we're going to prove the adequacy of the method. Okay, so we're going to start slowly here. We've seen that the tree method always gives a yes or no answer to the question, is this argument valid? So if we have an argument and we say, is this a valid argument? Truth functionally valid argument. We always get a yes or no answer. To say that the method is adequate is to say that the answer is always correct. So what we're doing here is that we're moving up a level of abstraction, and we're proving that our method for proving things, such as this argument is valid, this argument is invalid, this set is consistent, this entailment does or doesn't hold, we're moving up a level of abstraction, and we're going to be proving that this method of proving things actually works. It does what we're using it to do. This is something that we've been taking for granted, but now we're actually going to prove it, and we're going to prove it in a rigorous way, and the proof is going to be a proof by mathematical induction. And we'll think for a moment about why would we need mathematical induction for this. So remember that we test for the validity of an argument by testing the consistency of the set that has as members the premises and the negation of the conclusion of the argument in question. And note that the answer, no, the argument is invalid, happens if and only if there's an open path in the appropriate completed tree. So since an argument is invalid, if and only if there's a counterexample, that is, there's a truth value assignment that makes the premises true and the conclusion false, that is, the negation of the conclusion true, what we need to show in order to prove adequacy is this. And on the handout, I labeled this proposition number 1, but I'll write it down here. There is an open path branch, through a completed tree if and only if, this is a biconditional claim, some truth value assignment, there is a truth value assignment, makes all the initial sentences true, the set members true. I'm going to call the set members the initial sentences, the ones that we label SM. So this is what we need in order to prove the adequacy of the tree method. It is a biconditional, and we're going to prove the only if clause of this biconditional actually by proving something stronger than the claim. We're going to prove a stronger claim, and you'll see what I mean by that in just a moment. So for the only if direction, which is from that direction, we're going to prove what I'm calling proposition number 2. Each open path or branch, I'm calling them paths for some reason, path in a completed tree yields a truth value assignment on which not just the initial sentences are true, but every single sentence on that path is going to turn out to be true. So each open path in a completed tree yields a truth value assignment on which all sentences on the path are true. So I hope you see the sense in which I'm calling this a stronger claim than what we need to show in order to show the only if direction for number 1. Because number 1 says that if you've got an open path through a completed tree, it's going to give you a truth value assignment that makes the initial sentences true. We're going to show this stronger thing. We're going to show more than that. We're going to show that if you've got an open path in a completed tree, it's going to give you a truth value assignment that gives every single sentence on that path, that makes every single sentence on that path true, including the initial sentences, but the other sentences as well. Okay, so that's the only if direction. For the if direction, going the other way, we're going to prove proposition number 3, which again is a little bit stronger than what we need to prove in order to prove proposition number 1. And proposition number 3 tells us that given a truth value assignment, let me abbreviate that, truth value assignment that makes the initial sentences true, that is, if the initial sentences form a consistent set, that is, there's a truth value assignment that makes each member of the set true. It's a truth value assignment that makes all the initial sentences true. Given a truth value assignment, it's the old thinking and writing does not do well with me. Okay, let me start over. Given a truth value assignment that makes all the initial sentences true, we can find a path or a branch through the completed tree on which every sentence is true on that given truth value assignment. Every sentence on the path, every sentence is true on the given truth value assignment. Okay, but what we need to show for the if direction, looking back at proposition number 1, which is ultimately what we want to be showing, we're going to be showing that by these two parts. We have the only if and we have the if direction. What we need to show for the if direction is that if you've got, looking at the right-hand side of this biconditional, if you've got a truth value assignment that makes the initial sentences true, then there will be an open path through the completed tree. And so we're showing something a little stronger than that. We're saying given a truth value assignment that does make the initial sentences true, we'll be able to find a path through a completed tree, an open path through a completed tree, that on which every sentence is true on that truth value assignment. So we're showing, again, something a little bit stronger than we need to in order to show the if direction of proposition number 1. Obviously, when I say we find a path on that open tree, it's going to be an open path, right? Okay. Okay, so we're going to be proving number 1 by proving numbers 2 and 3. So I hope it's clear to you that if we can prove number 2 and we can prove number 3, we will have shown number 1 to be true. So that's our game plan, so to speak. So I hope that you have a copy of the handout to look at as I go along, because now I'm going to scroll up and this will disappear for a moment anyway. We can always access it again. How are we going to do this? Okay, so this is a significant result, and often when you're doing the proof of a significant result, there's some preliminary things you need to do first. And so that's the case certainly with this proof. So I'm going to look at some preliminaries. So the proof of adequacy, proof of propositions 2 and 3, and hence proposition 1, is going to depend on the fact that each one of our decomposition rules is correct in 2 different ways. Okay? They're correct, they're upwardly correct. So what we want to talk about now is the correctness of the rules, of the decomposition rules. There are 9 of them, remember. And rules can be correct in 2 different ways. And both of these kinds of correctness are going to play a really significant role in our adequacy proof. Okay, so just a little bit of terminology for this preliminary part of the proof. I'm going to take a look at I'm just going to arbitrarily choose an example of a decomposition rule, say the biconditional decomposition rule. I'm going to call the compound that we decompose when we apply a decomposition rule the premise of the rule, not to be confused with the premise of an argument. And when I apply the rule, if I apply the biconditional decomposition rule, I get on the left P and Q, and I get on the right not P and not Q. And I'm going to call these the lists of conclusions of the rule. Okay? And we say that a list of conclusions is true. We're going to think about lists as being true or false. A list is true when all the sentences in the list are true. That is, on a truth-value assignment. When I talk about truth, obviously I'm talking about truth with respect to truth-value assignments. And a list is false. All of this is in the handout. If even one sentence on the list is false. Okay. So let's look at this biconditional decomposition rule just by way of example, okay? And now I'm going to give you, I'm going to define these 2 types of correctness. First, I'm going to define downward correctness. So a rule, a decomposition rule, is downward correct So there's a definition, so it's going to be a biconditional claim. A rule is downward correct if and only if every truth value assignment that makes the premise of the rule true makes at least one list of conclusions true. So let's, before I define upward correct, which is the second kind of correctness, let's just take a look at this biconditional decomposition rule. And what does it mean to say that it's downward correct? What it means is that a rule, so this rule is downward correct if and only if what? Every truth value assignment that makes the biconditional, the sentence that has the form of a biconditional true, is going to make at least one of these lists true. And if you think about the characteristic truth table for the biconditional, it should be pretty clear that the biconditional decomposition rule is downward correct, right? So if a truth value assignment makes a biconditional true, it's going to make the two sentences true, or it's going to make the two sentences false. It comes directly from the characteristic truth table. And I think that if you just sort of go through the other 8 decomposition rules, you're going to see that, well, yeah, they're all downward correct. Let me talk about upward correctness, and then we can look at another rule, perhaps. Okay, so the second kind of correctness is upward correct. And we say that a rule is upward correct if and only if every truth value assignment that makes at least one list of conclusions true makes the premise true. So let's go back to the biconditional decomposition rule. Can I fit them both in the same screen? Yeah. Okay. So is the biconditional decomposition rule upwardly correct? Is it the case that every truth value assignment that makes at least one list of conclusions true makes the premise of the rule true too? Well, yeah, any truth value assignment that makes P and Q both true is going to make the biconditional true. And any truth value assignment that makes the two sentences false is going to make the biconditional true. We know that from the characteristic truth table for the biconditional, right? That's what we mean by the biconditional. So certainly the biconditional decomposition rule is both downward correct and upward correct. I mean, another way of thinking about this is that we need to observe, and actually this would require a rigorous proof by mathematical induction, which I'm not going to do, but I think we can just sort of convince ourselves at this point that all 9 of our rules have both of these properties. They're both upward correct and downward correct. Let's take a look at just another one. How about the decomposition rule for conjunction? It looks like that, right? So what does it mean to say that it's downward correct? It means that any truth value assignment that makes a conjunction true, well, there's only one list of conclusions. This is a non-branching rule. So any truth value assignment that makes the conjunction true is going to make both P and Q true. What does it mean to say that it's upward correct? Any truth value assignment that makes P and Q true is going to make the conjunction of P and Q true. So it's both upward and downward correct. Another one, P or Q, the rule looks like this. To say it's downward correct is to say that any truth value assignment that makes the disjunction of P or Q true is going to make at least one of these true. This list only has one, these lists have just one item in them. So any truth value assignment that makes the premise true, that makes this disjunction true, is going to make at least one of P and Q true, and it leaves open the possibility for it making both of them true. Okay, and what does it mean for it to be upward correct? Any truth value assignment that makes at least one of these true, suppose it makes P true, well, it's going to have to make P or Q true. And if it makes Q true, it's going to make P or Q true. Again, from the characteristic truth tables for both disjunction, conjunction, biconditional, and so on. So you can sort of run through the other, we've looked at 3 of them. You can run through if you want the other 6 of them, and it's not hard to convince yourself that the rules are both upward and downward correct. So a decomposition rule is both upward and downward correct if and only if the truth value assignments that make the compound true are precisely the truth value assignments that make at least one list of conclusions true. And that's something that wouldn't be hard to convince yourself of. Okay, so that's the preliminary stuff I wanted to talk about. And I want to reassure you once again that I'm never going to ask you to reproduce this proof. This is a significant proof. I want you to be able to follow along with it. I want you to have a good sense of what it means to say that a rule is upward correct, what it means to say that a rule is downward correct. And as we continue in this proof, I want you to have a good grasp of the roles that upward and downward correctness play in the proof. So we're going to continue. So now we're going to prove what I called proposition number 1 up here, that there's an open path through a completed tree if and only if some truth value assignment makes all the initial sentences true, which is what we were just assuming this to be the case as we applied the tree method back in chapter 4. We're going to prove that by proving propositions number 2 and 3. So let me write down another way of putting proposition number 2. So number 2 is each open path on a completed tree, and you guys all you remember what it means for a tree to be completed, that everything that's decomposable has been decomposed, or another way to think about it is that every sentence on the tree is either checked or is a literal. Each open path on a completed tree describes or yields a truth value assignment on which all sentences on the path are true. So this is if we prove this, we will have proven half of the adequacy. Each open path on a completed tree describes a truth value assignment on which all sentences on the path are true. Okay. So what I'm going to do, before I do the details of this proof, I want to give you kind of sketch the proof. The proof is by mathematical induction. And before I do sketch the proof, I want you to think for a moment, why would we need mathematical induction to prove this? Remember that mathematical induction is a proof technique that we use to show that the members of an infinite set all have a certain property. What's infinite about these trees? The trees aren't infinite, right? We're always testing finite sets of sentences. So our sets always have a finite number of members that we're testing. And the trees trees are not infinite because after sometimes they feel like they go on for too long, but once there are a finite number of sentences, we decompose them, and there are going to be a finite number of decompositions, and eventually we'll get to the point where everything's been decomposed, that's decomposable, and all we've got left are check sentences and literals. So why would we need mathematical induction for this? What's infinite? By the way, coming attraction, after we finish this interlude, we're going to be moving on to chapter number 7, and we're going to be learning a new language, excuse me, the language of predicate logic, and we're going to be expanding our tree method to cover sets of sentences in this new language of predicate logic, sometimes called quantificational logic. And the coming attraction is that those trees can be infinite. I want to actually ask you to construct an infinite tree, but theoretically they're infinite trees in what we're about to look at next. But for sentential logic, our trees are all finite. So why would we need mathematical induction? Well, it's not so much that we're going to have an infinitely long path, but we want to show that no matter how many sentences we check, that we decompose in the construction of this path, this is going to be true. So what we're imagining is that so we have our set members, our initial sentences, right? And what we want to show is that if you've got a completed open path through this tree for this set of initial sentences, that it's going to give you a truth value assignment that not only makes your initial sentences true, but it makes every single sentence along the path true. That's what we want to show. Okay? That's what's going on in this proposition here, which the proof for which I'm about to sketch out for you. Okay, so why would we need mathematical induction? It's not that we're going to be decomposing an infinite number of sentences in the construction of this path, but we want to show that no matter how many sentences we do decompose, whether that be 1 or 2 or 3 or 8,757,000, yes, theoretically, that could happen, right? No matter how many sentences we decompose in the construction of this path, this is going to be true. That it's going to give us a truth value assignment. What do I mean by a path describing a truth value assignment that makes the sentences true? What I mean is you collect the literals from that open path, and those literals describe a truth value assignment. And so what we're saying is the truth value assignment that those literals describe will make every single sentence on that path true, including the initial sentences, because they are common to the path as well. Okay, so that's what we're up to, and that's why we need mathematical induction, because we want to have this general proof that no matter how many sentences we had to decompose when we constructed this open path, it's going to yield a truth value assignment that makes every single sentence on the path true. Okay, my handwriting's a little sloppy there. Okay, so the truth of this, now I'm going to sketch this, right? And then I will do at least this part of the proof, the proof of proposition number 2. I'm going to take you through all of the details of the proof by mathematical induction later. But right now I just want to kind of sketch it for you so you have an idea of how the proof is going to go and how mathematical induction is used. So the truth of proposition number 2 is going to depend on the upward correctness of the rules. The proof of proposition number 3 in the other direction is going to depend on the downward correctness of the rules. By this point, we've convinced ourselves that all of our rules are both upward and downward correct. What does it mean, again, for a rule to be upward correct? It means that every truth value assignment that makes at least one list of conclusions true, that makes something that was generated by an application of the rule, every truth value assignment that makes that stuff true is going to make the compound true. So every truth value assignment that makes, say, P true is going to make P or Q. Every truth value assignment that makes Q true is going to make P or Q true, and so on with the other decomposition rules. Every truth value assignment that it makes at least one list of conclusions true, say that makes P and Q both false, is going to make P if and only if Q true. Okay, so this part of the proof, that if you have an open path through a completed tree, it's going to give you a truth value assignment that makes all the sentences on the path true. That's going to depend on the upward correctness of the rules. Okay, so the truth value assignment described by an open path through a completed tree is going to be one on which an atomic sentence is going to have the value true or false, depending upon whether its negation appears as a line on the path, right? So I'll draw this sort of, I don't know whether this is a helpful image or not, but I'll draw the little thing I drew before. So here you've got, you've got your tree, and here you're focusing on this open path through a completed tree. Okay. The truth value assignment that this open path describes is going to be one on which an atomic sentence is going to have the value true or false depending upon whether it appears or its negation appears as a line on the path. So for instance, if A appears, then the truth value assignment is going to assign true to A. If not B appears, then this truth value assignment that the open path describes is going to assign false to B, and so on. So we know that, sort of by definition, every literal on that path is going to be true on the truth value assignment described by the path, right? Because you also know that if this is a completed open path, you know that it's got to have at least one literal. If it didn't have a literal, then it wouldn't be completed. Okay, so we know that the literals are all, the literals are all true. The literals on the path, on the open path through the completed tree, are all true on the truth value assignment the open path describes. Okay, that's going to kind of be our base case. Remember that mathematical induction, proofs by mathematical induction have two parts. They have the base case where you want to show that the claim is true for the smallest member of the set, the first member of the set, and then it has the inductive step, which is a conditional claim that if some arbitrarily chosen member of the set, say the kth member of the set, it has the property, then the guy after it, the k plus first member of the set, has the property. Okay, so, but again, I'm just kind of sketching this out now, right? So you know that the literals that appear on that path are all going to be true on the truth value assignment that the open path describes, just sort of by definition. Okay, moving on. Since that path is open and the tree is completed, any sentence that's longer than a literal that occurs as a line on that path must have been checked. It must have been decomposed, right? So if there's some other sentence that's bigger than a literal on that path, in order for that path to be a completed path, it must be checked. It must be decomposed, right? And so it must have at least one list of conclusions on that path, right? It might, when you decompose this, it might have branched, but you know that if it appeared on this path that we're focusing on, it's got to have a list of conclusions on that path, and the conclusions that it generated are going to be shorter than the thing that you decomposed, right? So since the path is open and the tree is completed, any longer sentence, longer than a literal, that appears as a line on that path must have been checked, that is, decomposed, and it must have a list of conclusions on the path, and each of which is shorter than the checked compound, the decomposed compound. So among those checked sentences, there must be one or more that have only literals as conclusions on the path, right? Because we're imagining that there are some literals on this completed open path. Where do they come from? Well, maybe they're just set members. So the simplest case would be, suppose our set members were A and B. Well, there's a completed open tree, right? It's got one path. Nothing had to be decomposed in the construction of this tree. But if we had a more complex tree where something compound had to be decomposed and checked, eventually there's going to be some compound that yielded as a list of conclusions something that involved literals, right? Okay, but and those literals, as we've seen, sort of by definition, are going to be true on the truth value assignment described by the open path. Okay, but since our rules are upward correct, we know that every checked sentence must be true on the truth value assignment that we recover from the tree, because it has a list of conclusions on the path that's known to be true on the truth value assignment. So just to kind of give you something, a more concrete thing to look at. Suppose, we're looking through this open path on the completed tree, right? And suppose that on that path was A and B, and we decomposed it and we got A and B. Well, we know that A and B are true on the truth value assignment described by the open path by definition, right? And we also know that since our rules are upward correct, the sentence that was decomposed that generated them, right, the premise of that rule, by the upward correctness of the rule, is also true on that truth value assignment. And if A and B was generated as a list of conclusions from something more complex that had been decomposed before, then by the upward correctness of the rule guarantees us that since the conjunction of A and B is true on the truth value assignment, then the thing that generated it by application of an upwardly correct rule is true on the truth value assignment. And you work your way all the way up the path until you've convinced yourself by the upward correctness of the rules that every sentence on that path is true. So that's kind of what's going on here. So we continue reasoning this way until we've accounted for all of the checked sentences on that path. So among the sentences we already know to be true on the truth value assignment described by the path, may be a list of conclusions of some sentence whose truth value assignment hasn't been established, right? So there might be something up here. But the upward correctness of the rules guarantees that if it makes the thing that it generated true by application of an upwardly correct rule, then it's going to make the thing that was decomposed true in that truth value assignment as well. So since the rules are upward correct, the sentence must already be true on that truth value assignment because its conclusions are true on the truth value assignments. Okay, so that's kind of the sketch of the proof. I hope that's clear. And this is the level on which I want you to have a grasp of this proof. I'm gonna take you through the details of this proof by mathematical induction, but this is the level that I want you to understand at least this half of the proof. Then we'll talk about the other half of the proof. And now I'm trying to decide whether I should continue and do the proof. I'm going to, because you could always stop this lecture now, take a breath, go for a walk, come back, and then listen to the rest of it. So I'm going to continue with this. And now what I'm going to do is actually do the proof that I've sketched out here. I'm going to do that proof by mathematical induction. I'm going to take you through the details of the proof by mathematical induction. Okay, so that was just the sketch to give you the idea of what's to come. Okay, so we are going to prove proposition number 2, which is half of proposition number 1. It's going to be half of our adequacy proof. We're going to prove this by induction on the number of checked sentences on the path under consideration. Remember, I said that we wanted to convince ourselves that no matter how many sentences we have to decompose on this open path through a completed tree, it will be the case that the truth value assignment described by that open path will make every single sentence on that path true, no matter how many sentences we may have decomposed in the construction of that path. Okay, so the proof of number 2 is going to be by induction on the number of checked sentences if you can just like relax and enjoy this, you can enjoy it, I think, rather than worrying about, oh my goodness, what is she doing? What are we going to, is it going to be on a quiz? Just relax. Try to enjoy. This is kind of a cool proof, okay? And it's also, you know, proofs by mathematical induction are kind of weird, and this has the same property of weirdness. Okay. Proof of proposition number 2 is by mathematical induction on the number of checked, that is decomposed sentences on that open path under consideration. What do I mean by the path under consideration? What I mean is this, talking about, you know, take an open path through a completed tree, we're going to show that it describes a truth-value assignment on which all sentences on the path are true. Okay. And what do I mean by induction on the number of checked sentences? What I mean is that no matter how many sentences have been checked in the construction of that tree, it's going to be the case that that path describes a truth-value assignment that makes every sentence on the path true. Okay. So, the proposition that I'm going to sort of rewrite proposition number 2, I'm going to call it number 4. This is what we're going to show. We're going to prove number 2 by showing number 4, and that's this proposition. It's going to sound a lot like what I just said, but I'm going to write it down. The truth value assignment described by an open path with n checked sentences. There are n sentences, n checks on that path in a completed tree. The tree is completed. Will force the value true on every sentence that appears as a line, as a full line on that path. Okay? This is what we're going to show. If we can show this, we will have shown number 2, which means we will have shown the only if direction of what I called proposition number 1 at the very beginning of the lecture. Okay, remember, stepping back, try to remember what we're doing, don't get lost in this thicket. We want to show there's an open path through a completed tree if and only if there's a truth value assignment that makes the initial sentences true. In other words, we're showing that the tree method does what we're using it to do. And here's where we've gotten ourselves. We've gotten ourselves to the point where we need to show proposition number 4 to be true, and we're going to show that by mathematical induction. A truth value assignment described by an open path with n checked sentences in a completed tree will make every single sentence that appears on that path true. Okay, and the proof, again, is by mathematical induction, and it's got 2 parts. So first we're going to show the base case. Remember that the base case of a proof by mathematical induction is we want to show this, you know, no matter what number n we have here. And n is going to be a natural number. So n is going to be 0, 1, 2, 3, and so on, right? So the base case here is going to be the case where n is 0. That is, no sentence has been checked. 0 sentences have been checked in the construction of the path that we're looking at. Nothing's been decomposed. And what we want to show that if nothing has been decomposed, if 0 sentences have been decomposed in the construction of this path, then every sentence on the path is going to be true on the truth value assignment described by that path. Okay? We'll come back to that in just a moment, but just to remind you of the other step in a proof by mathematical induction, it's called the inductive step. And that is, if 4 is true, proposition 4 is true for some arbitrarily chosen n, then it's true for n plus 1. That is, if it's true that if you've checked n sentences in the construction of the path, then it's true, you're going to show this. If it's true that it's true for n sentences being checked in the construction of the path, then it's true for n plus 1 sentences being checked in the construction of the path. Okay? And if we can show both of these, then we've shown that 4 is true by mathematical induction, that no matter how many, whether it's 0, 1, 2, 3, 7 million sentences have been checked, the truth value assignment that the open path describes will make every single sentence on the path true. Okay, let's go back to the base case. Okay? Suppose that no sentence has been checked in the construction of the tree. So n equals 0, right? I'm just going to, for the moment, erase this just so I have room to prove the base case in the same screen. So what does that mean? What would a tree look like where no sentences have been checked at all? Well, if no sentence has been decomposed, well, then that path has to be the whole tree. And all of the set members, the initial sentences, have to be literals, right? So the only way that you're going to have, so here would just be an example, the only way that you're going to have a completed tree with an open path where nothing has been decomposed is if the set members are all literals, right? And if the set members are all literals, see, so n equals 0, nothing's been checked. If the set members are all literals, then just sort of by definition of the truth value assignment described by an open path, it's going to be the case that all of the sentences are going to be true on that truth value assignment, because that's where we get the truth value assignment. It's designed to make the literals true. So in this case, proof of the base case is, remember I said that often the mathematical inductions, proofs by mathematical induction, the base case is kind of obvious. In this case, it is kind of obvious. So if 0 sentences have been checked, then all the initial sentences are literals. So all the sentences are true on the truth value assignment described by the open path. Okay. Should I have broken this up into 2 lectures? Yeah, maybe, but I'm going to continue. But you can stop it. You can see it as 2 lectures if you want to. Okay. The inductive step, that's more interesting. The inductive step of the proof by mathematical induction. We want to assume that proposition number 4 is true for some arbitrarily chosen natural number n, okay? And we want to show that proposition number 4 is true for n plus 1. What does this mean? We're going to assume that if you've got an open path through a completed tree where n sentences have been checked, that the truth value assignment described by that open path is going to make every single sentence on the path true. That's our, what we might call our inductive assumption. remember that the inductive case involves showing a conditional going to be true. So this is sort of the antecedent of that conditional, and this is the consequent of that conditional. We need to show that it's true if one more sentence had been checked in the construction of the tree. And again, upward correctness is going to play a really significant role in this part of the proof. Okay. Take a break if you want. Go take a walk. Come back. I'll still be here. Okay. So how are we going to do this? We're going to focus on an open path through the original tree that's got at least n+1 checked sentences. Okay? So we've got an open path through our tree, and there were n+1 sentences have been decomposed. Okay, so by our hypothesis, by our inductive hypothesis, this path has to have at least one checked sentences, right? Because it has n+1 checked sentences where n is greater than or equal to 0. So even if n is 0, n+1 is 1. So we know that something, at least one thing, has been decomposed in the construction of this path. So what we're going to do is we're going to consider the first sentence that was checked in the construction of this path. The first sentence that was checked in the construction of the path has got to be an initial sentence. Do you guys see that? The first sentence that we checked or decomposed in the construction of this path that we're looking at, this open path through the completed tree that's got n+1 checked sentences, where n is 0 or 1 or 2 or 3, so construction of the path. Do you see that the first sentence that you decomposed has to be a set member or an initial sentence? That's how you got the ball rolling, right? It's not like, oh, you've got your set members and you decompose something down here. No, when you decompose, it's got to have been an initial sentence that was checked first. So let's consider this first sentence that was checked in the construction of this open path through a completed tree. It was a set member. So now what we're going to do is that we're going to lop that sentence off. We're going to delete that sentence from our tree and look at what remains on that path. If we get rid of that sentence, then what remains is a path that has n checked sentences. Because we've deleted the first sentence that was checked in the path that had n+1 checked sentences, n+1 minus 1, right? We deleted this guy. So the rest of this path has n checked sentences. Okay. Now we're going to consider this diminished path. This diminished path that has n checked sentences, not n, that has n checked sentences, not n+1 checked sentences. Okay, so think about the diminished path that we got from the original chosen path. The diminished path, again, was gotten by deleting the first sentence that was checked in the construction of the tree. There are exactly n checked sentences on this diminished path. And note that among the sentences on the diminished path are going to be all the members of one list of conclusions that were added to the tree when we decomposed that first sentence. Okay, so now what I'm going to do is I'm going to give you an actual concrete example so that you can wrap your mind around this. This is just an example. This is like it's a visual aid because what we're doing is a general proof, but here's a visual aid, an example. So suppose we had this tree. Our initial sentences were A, horseshoe, not A, horseshoe, A, horseshoe, B. So that was initial sentence. And then the next one was A. So those were the initial sentences of our original tree. These are the initial sentences. You know, just bear with me because this is cool. You'll feel good. It'll be good for your something, soul, mind, to hang in there with this. Okay. So these are the initial sentences of the original tree. Okay. Now I'm going to construct the rest of this tree. So what I'm going to do is I'm going to decompose line number 1. So that's going to give me line number 3. And I have A, horseshoe, not A on the left. Oh, sorry, the negation of A, horseshoe, not A on the left. And then A, horseshoe, B on the right. So this was the first sentence that was checked in the construction of the tree. I'm not going to write down all of the justifications over here. I'm just going to do the tree. And then when I decompose line number 3, and this is in the handout as well, okay? I get A and not A, okay? And then what I didn't do in the handout was decompose line number 5, so let me do that here. I get that. So I applied double negation decomposition to line number 5, and I get that. And now I'm going to decompose on the right, and I'm going to have on line number 7, not A and B on the right by application of conditional decomposition to line number 3 on the right. Okay, so lines number 1 and 2 are the initial sentences of our original tree. And the path that we're looking at, oh, by the way, that closes, right? The path that we're looking at, we're focusing on, remember we're in this proof, we're looking at, we're focusing on an open path through a completed tree. Here is a completed tree. We're focusing on this path, this open path through the completed tree. And so that path is this one, right? That's the path we're focusing on. And that path, we're imagining, has n+1 checked sentences. Right? I meant to check that. I didn't check these. Okay, n+1 checked sentences. So now I'm going to do what I was talking about up here. I'm going to delete the first sentence that was checked in the construction of this open path, and that is this one, right? I'm going to lop this guy off, okay? And now I'm going to, the first thing we need to see is that the result of lopping that off, which is what now I'm putting around in red here, this actually is what I'm going to call the diminished. It's a diminished tree. It's the tree that I get when I lop off the first checked sentence in the construction of the tree and keep the remaining initial sentences along with the list of conclusions that was generated along this path by application of the appropriate rule to the first sentence that was checked. And so what I've circled in red here is actually a completed tree. And the initial sentences of this diminished completed tree are the ones that I've just circled in green. So these are the initial sentences, why am I doing this? You'll see in a moment, of the diminished tree. Okay? So what have I done? I have this tree. It's a completed open tree. I'm focusing on an open path through the completed tree. I'm assuming that that open path has n plus 1 checked sentences. I lopped off the first sentence that was checked in the construction of that path. When I look at what results here, after deleting that sentence, this is actually a completed tree that has an open path. The tree has this and that as initial sentences, and what I could have numbered this, call this say 2 prime. It has lines 2 and 2 prime as initial sentences, and then I decomposed line 2 prime and I got line 7 here. Okay? All right. So in the handout, I give sort of more specific explanation of what a diminished tree is, and I'm not going to go through that now because I think that will just kind of confuse matters. But so here is an example of what we were talking about here. And remember, we're trying to prove the inductive step, that if the proposition is true for n check sentences, then it's going to be true for n plus 1 check sentences. And what I did here, again, this is just kind of an aid, it's just an example, so you can sort of wrap your mind around what's going on in this abstract proof, just so that you can be looking at something to think about it, is here is our path through a completed open tree, our open path that's got n plus 1 check sentences. What is n? Well, n plus 1 was 2, so n equals 1. In this particular case, n equals 1, right? Because there were n plus 1 check sentences originally. We lopped one off. Now n equals 1. Okay. How do we finish up the inductive step? What we want to show is that given any open path through a completed tree where the path has n plus 1 checked sentences, the diminished path has n checked sentences. So in our example here, our original path had 2 checked sentences. Our diminished path has 1 checked sentence. What we want to show is that if it's true that the truth value assignment described by the diminished path, and what is that truth value assignment? For this particular path, it's the one that makes A true and B true. So that truth value assignment we're assuming makes every sentence on this path true, and by the way it does. Obviously if A and B are both true, then A horseshoe B is true. And on the basis of that, we want to show that it makes a path that has n plus 1 check sentences true. So what do? We add this back on. Once we put this back on to the path, and the result is a path that has n plus 1 check sentences. And so we have to show that if the truth value assignment described by the path with n check sentences, that this diminished path makes everything on the path true, then it's going to make the one that has n plus 1 check sentences true. Well, yeah, if we put that back on, by the upward correctness of the rules, since this was generated by an application of an upwardly correct rule to line number 1, we're guaranteed that line number 1 is also true on that truth value assignment. Ta-da! For this example. Okay, let's do this in a more general way. And you might be thinking, well, there's something fishy around here because you didn't just arbitrarily put another one up there. You put the one up that you had deleted. Well, yeah, that's kind of the the funny nature of proofs by mathematical induction. Of course, it's the one that we deleted. Okay, so we're going to finish up the inductive step. And you now have kind of this picture to wrap around. And again, it's in the handout. So given any open path through a completed tree where the given path has n plus 1 check sentences, the diminished path that has n check sentence is an open path through a completed tree. Namely, it's an open path through the diminished tree, as we were just talking about. So according to our inductive assumption, the diminished path yields a truth value assignment on which all the sentences on the diminished path have the truth value true. Among the sentences on the diminished path are going to be the members of one list of, I'm circling it here, one list of conclusions that had the deleted sentence as its premise, right? So this, the deleted sentence, was the premise that generated this sentence, right? So by the upward correctness of the rules of decomposition, the deleted sentence has to be true on the truth value assignment we get from the diminished path. And now we're almost at the end of the proof. Therefore, every sentence on the original path must be true on the truth value assignment we got, because we got the truth value assignment described by the path, because we got the diminished path from the original path simply by deleting a sentence known to be true on the truth value assignment that the diminished path describes by the upward correctness of the rules. So what we've shown is that if proposition 4 is true for n, then it's true for n plus 1. And it does have this kind of mysterious nature. It's kind of, you know, it's a proof by mathematical induction. We showed the base case. If n equals 1, then proposition is number four is true. And if it's true for n, if proposition 4 is true for n, then it's true for n plus 1. So we've shown the inductive step to be true. So we've shown by mathematical induction proposition 4 to be true, where induction was on the number of sentences checked or decomposed along the path of the tree. Okay, that's kind of a lot of details, hard to wrap one's mind around. Read the handout, try to go through this again. But what I want you to grasp is what I did when I sketched the proof initially and talked about the rules being upward correct, the proof of proposition number 2, which became proposition number 4, and how the upward correctness of the rules is going to ensure that the literals on that completed open path are going to make every sentence on the path true. Okay, I'm going to stop here. I bet you're all pretty happy about that. The next lecture is going to be much shorter. I'm just going to talk briefly about the other half of the proof, and then say a little bit more about upward and downward correctness of rules, because this is an incomplete proof. What remains, and I will not do the details of this proof, what remains is the proof of proposition number 3, the other way around, that if you've got a truth value assignment that makes your initial sentences true, then it's going to make all the sentences on some path of the completed open tree true. Okay, I'm going to stop here. I hope you enjoyed that. Signing off for now.